Today's video is going to focus on the wave nature of matter. I'm going to strongly recommend that you read chapter 12.3 because I'm going to stop this video short of going over the many different interpretations of quantum mechanics, the interpretation of the double slit experiment. There's three specifically that's focused in this textbook chapter, and that's the Copenhagen interpretation, the many worlds interpretation, and the pilot wave interpretation. Please read those. At the very least, I'll make sure that there's some other videos down below by PBS SpaceTime. That guy does a really good job of explaining all three of them. He will go over a lot of the theory that I went over in the last video and some of the theory that I went over in this video. So you'll basically hear the same thing a few different times, which is probably good for trying to remember what's actually happening. And it'll make more sense the more times you hear it, if it can make sense whatsoever. A slightly different version of these notes can be found on May 29th, and they have a bit more details because I've deleted a bunch of the slides. But yeah, make sure you actually watch those videos, or at the very minimum, read the couple pages about the many different interpretations of quantum mechanics. So last video was all about how, started off in grade 11, how light behaves like a wave. We spent a lot of time on that in grade 11, looking at the wave-like properties of light. And then it turns out light can also behave like a particle, and therefore we have the photoelectric effects, right? The kinetic energy of electrons that are emitted is dependent on the actual incoming energy of the light itself, minus the actual work function of the very specific metal. And so therefore it must behave like a particle. It must be a particle. So that's kind of what the thought was. And that would mean that these photons are having collisions. And typically, if you're looking at collisions, you're dealing with momentum, yet photons don't have mass. So it was shown that although photons don't have mass, they can possess momentum, especially if you combine that with Einstein's special relativity. And you ended up with a little equation for momentum. And of course, that's based on its wavelength, or you can replace the wavelength with the universal wave equation and get frequency in there and the speed of light. So there's two different versions of this equation. I just typed that one out. So if photons behave like a particle, experiments were done, and it was determined that there are 5 different interactions where it behaves like a particle. So interaction 1, you end up with coherent scattering. So a particle just might ricochet, a photon might just ricochet off an electron as it interacts with an atom. Kind of like if you threw a ping pong ball at a basketball that was at rest. The ping pong ball would just pretty much bounce off the basketball, might cause the basketball just to move just ever so slightly, kind of like how you see in this animation, sort of cause that electron to vibrate a little bit more, and then it'll just scatter off probably in a new direction. And that is one interaction between a photon and electron. Different interaction, well, we spent a little bit of time on this in the last video. So you have the photoelectric effect, the electron absorbs the photon and then just gets scattered out. Right, and so it leaves with momentum, it leaves with kinetic energy. That electron goes away, and yeah, I won't talk about that again because that was in the last video. The third interaction is kind of like the photoelectric effect. The difference is you have high energy photons. So we're now in the X-ray range, and so often when X-rays interact with electrons, so the electron will absorb some of that energy and get scattered out like it was the photoelectric effect, but there's still energy left over, and therefore the X-ray gets scattered off in a new direction. So this is what it looks like mathematically. Essentially, you end up with high energy X-ray interacting with an electron. It pretty much kicks the electron out, no different than what it would have in Unit 3 if we're talking about conservation momentum of, say, two pool balls. Maybe if they don't hit dead center, pool ball 1 would collide with pool ball number 2, and then pool ball number 1 would probably get ricocheted in a different direction. And that's kind of this, as pool ball number 2 goes up in an upward direction, I guess. The only difference is we're not talking about a pool ball with mass. We are talking about a photon, typically an X-ray photon with a specific frequency or wavelength. And after the interaction, the momentum of the photon would still be an X-ray, but would have a much less momentum than it would have before, and therefore it also have less energy than it had before, because some of that energy and momentum would have had to have gone into this electron as that electron gets scattered away. So conservation of momentum and conservation of kinetic energy is still a thing in this regard. Now, when I say kinetic energy, I just mean kinetic energy of the electron. Photons obviously don't have kinetic energy, because that would mean they'd have to have mass. So that was your constant scattering. The fourth interaction is kind of not much of an interaction. This is something you'll probably look into more in chemistry. So the electron might just absorb the photon for a brief period of time and then re-emit it. So when it does absorb that photon, it causes the electron to get to a higher energy state. So that could be an example of, I'll just use the diagram of this animation, might mean the electron would just go from an s orbital and move up into a p orbital for a brief moment in time before dropping back down into its ground state and then re-emit that photon. So that is the fourth interaction with matter. Fifth interaction of matter is known as pair production or pair creation, as I'm seeing more and more textbooks go into that name instead. And basically you end up with a really high energy photon. I have a little note here, typically greater than 1 million electron volts, interacting with the nucleus of an atom. And basically when that happens, it creates an electron positron pair, so matter antimatter pair. And this is used in PET scans, so positron emitted topography. So you'll see this interaction used in the medical industry. Well, hopefully you won't see it, because hopefully you're not getting scanned for any particular reason. But anyways, so for those 5 reasons, light must be a particle. Yet, we still have this issue. Particles shouldn't do that. Particles shouldn't undergo interference. So we know light undergoes an interference pattern. Light is showing particle effects. So what if we actually did the double slit experiment with particles instead of just saying, well, particles shouldn't be able to do that? That's not right. Particles can't do that, because we keep thinking it in terms of classical mechanics. So a bunch of physicists got together and thought, well, why don't we actually fire some electrons through the double slit experiment? And they did. They fired a couple, and they didn't really notice any discernible patterns. So they fired lots more, and over time, as they kept on firing more and more electrons through, they ended up getting an interference pattern, which is very puzzling, because that is only something that should happen with waves. And what this basically told physicists is, well, what do the electrons do? Do they split in half, and half of the electron goes through the top slit, half the electron goes through the bottom slit, and then they somehow do a diffraction pattern, then somehow do an interference pattern? I don't get it. What's going on? So that was very, very puzzling. It was hard to figure out what was actually happening here that was causing the electrons to just know to form the interference pattern rather than forming the classical pattern of just 2 slits. So they ran that experiment again with more electrons. They ran the experiment with protons, other atoms, other molecules even, so the particles got slightly bigger, and they all showed that interference pattern. So particles are showing wave patterns, so interference patterns, and waves, so light, for instance, lots of evidence that says it's a wave, somehow behaves like a particle, right? Light and other electromagnetic radiation will show particle-like behavior. So when you get to the quantum world, what we would think of classically no longer works. Newtonian physics breaks down at that quantum level. There is no real distinction between particles and waves. So that got a man by the name of de Broglie thinking that, well, maybe we can find the wavelength of particles. Particles must have a wavelength. Oh, I'm getting ahead of myself though. So 2 quick little things to point out as far as the wave-particle duality. All quantum objects, including electromagnetic radiation electrons, can exhibit interference, right? There's been a numerous amount of tests that prove this true. All quantum objects, including electromagnetic radiation and electrons, transfer energy in distinct or discrete amounts. So again, that is just known as quantum. So the wave-particle duality is born. Back to my original point, because I got ahead of myself. Louis de Broglie, so we pronounce his name de Broglie, not de Broglie. He's European, what do you expect? I forget if he's Belgian or French. Doesn't matter. Anyways, so he proposed that, okay, well, if we've got an equation to describe the momentum of a photon with respect to its wavelength, we can then take that equation and substitute in the actual equation for momentum if we solve for the wavelength, and we can actually get a wavelength for matter waves. So we can plug in the mass of the electron, we can plug in the speed of the electron and find out what the electron's actual wavelength is, since it is showing that matter has wave properties. Now, these wave properties are really only apparent to particles, because if you consider yourself, the mass of yourself, let's assume that you are at the very most, the heaviest, maybe you're 100 kilograms. So you're at order of 10 to the 2. Maybe you're traveling at highway speeds. In fact, I'll assume you travel a little bit faster. We'll call it 100 meters per second. Right? Maybe you're going you're in a race car, so you're going 100 meters per second. So at the very most, you're going to have 10 to the positive 4 by the time you're done this multiplication down there. Right? This, if we're talking about you in a race car traveling fast. If you consider this guy as an order of magnitude of 10 to the negative 34, if you have 10 to the negative 34 divided by 10 to the positive 4, you're at a level, a wavelength size of 10 to the negative 38 meters. So large objects have wavelengths that are just too small to even consider to be existing. It's not measurable. So that's why the Mac, you don't behave like a wave. You can't walk through 2 doors at the same time, right? Large objects don't show wave-like behaviors, but particles, you throw an electron in there, you got 10 to the negative 31, so that's pretty close to 10 to the negative 34 on the top, and so therefore you'll actually get values of wavelengths that are actually measurable. And so at the quantum realm of quantum world, we can actually measure and detect the wavelength of certain particles. So again, this was, I touched on this a little bit in the last video, but hyperphysics has a nice little walkthrough of how this came to be. So last video, I kind of walked through how to calculate the momentum, and I made mention how we tied in relativity to it. Basically, you can get the combine the energy with the speed of light to calculate your momentum. Combine that with the photoelectric effect, and this, voila, we've got an equation for wavelength photon involving momentum, and then all he did was just replace momentum of light photon for momentum of something with mass. So we know this works because since that realization, we've created scanning electron microscopes where we've used the wave nature of the electron to actually create images, really high resolution images of really small things. And basically, it's not going to give us an image that we can immediately look through a telescope, right? So what's happening is you have electrons being fired at whatever your specimen is, and those electrons will ricochet and scatter off, and what they do is they measure the energies of the electrons that were scattered off, and they run it through a computer program to actually simulate the diagram of what they were looking at. And it gives really high resolution images, really very detailed images of things that are really small. So I like the salt and pepper one because it literally looks like boulders and tree bark, which is what salt and pepper is. It's just the grains of salt are really, really, really tiny. But through a scanning electron microscope, it seriously looks like a bunch of trees and tree bark and boulders, or just rocks. Human tongue looks like a cat in the scanning electron microscope. And it gets such insane amount of detail. Kidney stones, we can see why they hurt so much. Look at all the jagged crystal edges. And of course, biologists love it because they can see really small images to extreme detail. And I do like how they often get artists to paint them as well, because typically they're going to be in black and white. So these aren't true colors, obviously, but they just get artists to paint and just colorize it a little bit. And I do like the way this one looks because it reminds me of Wallace and Gromit. That's the type of images it does produce, but you can see all the different pores of really small creatures that you wouldn't be able to see with ordinary microscopes. So here's the math part. So let's just do a quick little example. If an average wavelength of visible light is somewhere around the green spectrum, all right, so if I take all the wavelengths of visible light and just do the average, you're somewhere around 550 nanometers. How many times smaller is an electron wave if it's traveling at 2/3 the speed of light. So just to give you an idea of how much better a scanning electron microscope will be as far as resolution. So if I find the wavelength of the individual electron, I'll need to know the mass of the electron. So for that, again, you just have to look it up on the chart, 9.11 times 10 to the negative 31, multiplied by 2/3 the speed of light, all in the denominator. So 2/3 the speed of light would technically just be 2 times 10 to the 8 meters per second, but I just put it all in there in one equation. Work the math through, you end up with roughly 3.64 times 10 to the negative 12 meters. So that's in the picometer realm. If I want to know how many times smaller this is, I would just take my average wavelength of visible light and just do a division. And you'd end up with somewhere around 151,000 times smaller. So that gives you an insane amount of resolution when you're trying to look at something really small. So biologists love it because they can see all the little nooks and crannies of really tiny organisms, or at least parts of a larger organism that they're trying to establish why the pigment of a butterfly is the way it is, for instance. Geologists like to use it for determining just shapes of minerals and structures. Yeah, I'll just touch on those two. Great for the medical industry as well. So it gives you really, really small images and try to find out the root cause of certain things. So because we now know that electrons show and matter in general show wave-like behaviors, we have to kind of redefine how we view the model of the atom. So very often we're still going to use the Bohr-Rutherford model of the atom, especially at the younger introductory grades, because it's just a bit easier to visualize, the planetary model. Right, electrons are going around it's not accurate, but it's close enough. And so we tend to go for clarity rather than accuracy when it comes to describing this stuff. But this is closer to what the atom actually looks like. In fact, I've got a little shockwave flash file here that I tend to like to show to my students because it really kind of paints it a bit better, a bit clearer, I think. So this is kind of how we view electrons just traveling normally. But if we consider the fact that they have wave-like behavior, thanks to de Broglie, and you combine that with the planetary model. So again, planetary model, we believe the electron was just going around the nucleus of the atom. So this is your basic hydrogen atom, if you will. So a single proton, but you can call this whatever atom you want. If we combine this and show the wave behaviors, we know that as it's undergoing every crest and trough, that technically means that the electron is going to sometimes appear closer to the nucleus of the atom, and sometimes it's going to be further from the nucleus of the atom. Now, this is just 2-dimension. I don't have a 3-dimensional representation, but if you consider in 3 dimensions, you basically have an orbiting orbit, if you will. It sounded dumb to say out loud, but that's kind of the idea if we're only limited to dimensions. So really, the electron shows a big cloud of where it could possibly be. It's no longer, oh, the electron's along this dotted black line here. It says, no, it's not. It's somewhere in this region at any given point in time, which now means we have a probability. And thus, the planetary model was replaced with the probability model, otherwise known as the electron cloud. So this is known as a cloud distribution. Where it's darker is probably a higher statistical probability of where we can actually find the electron. Where it's brighter and whiter, that's a low statistical probability of where we can probably find an electron, right? It's not a 0 probability, it's just very low and unlikely to find the electron here. Likely to find it here. So if we go into all the higher orbital levels, it'll take on different shapes. So the second wave orbits 2 wavelengths long. It probably look like this, more of an elliptical shape as it orbits around, right? It still creates a bit of a cloud there. As we go into higher order levels, so again, the third orbit, if you will, 3 wavelengths long, right? It takes on the fidget spinner approach, especially if you put it into motion, right? It's 3 wavelengths long. 4th orbit, 5th orbit, 6th orbit. I think at this point you get the idea of all the different wavelengths. So again, you're just seeing a bunch of electrons in that electron cloud. So this is kind of the simple diagram if we're trying to represent the electron cloud, but for the most part, oh, I deleted that. For the most part, it's just kind of drawn as a haze. nowadays without showing all the actual possible paths, because we know that, you know, there's still a likelihood that, say, this red path could be found here. So often it's just drawn with a nucleus and a fuzzy haze around there to represent the de Broglie atom of quantum mechanics. So if we go back to the double slit experiment, so we're talking about particles. How do we know which slit the particle is actually going to go through? All right, so if you actually just let it go on its own, it will form the interference pattern. But physicists like to be able to measure things. We like to know things accurately. So if you actually measure it, so by putting some kind of detector right behind one of these slits, because we want to know which one, how does it know which slit to go through? How does it know which path to take? We have to be able to measure that stuff. So if you physically measure it, right, maybe not with a visible camera, it might just be some other type of detector that can detect electrons, the very act of measuring it causes the wave function to collapse. And you're no longer sending a particle with wave properties, you are just sending a particle through. And this is the pattern you'll get. Suddenly, once you detect it, once you are making measurements, particles will behave classically. If you turn the detectors off and no longer make measurements, particles behave the way quantum mechanics predicts. Particles will behave with wave-like properties. Turn it on, you're back to classical. Turn it off, you're back to quantum. So this creates an issue because you cannot make measurements at the quantum level without directly affecting the experiment. So when not observed, the particle behaves according to the wave function. So that creates issues, which brings about the two golden rules of quantum mechanics. Rule one is a superposition principle, which basically says a particle can be here or there, right? That's where we can expect to see the particle. That's if we're measuring it. Quantum physics allows it to be here and there. It can go through, quantum physics says that when you're not measuring it, the particle goes through both slits simultaneously and remains in a superposition until it makes a collision with the actual wall in which we're making our observations. Rule number two, I like a lot. It's very simple. The measurement principle. Rule one only works if you don't look at it. As soon as you measure it, the wave function collapses and it no longer is in a superposition. So if you measure it, you disturb it. It sounds silly, but that's kind of where quantum physics leaves us. So that introduces us to a man by the name of Werner Heisenberg. Looks like this, if you will, right? He's not a meth dealer in that show Breaking Bad. He's an actual physicist. The very act of trying to measure the position of electron affects its momentum, and likewise for the momentum. So his uncertainty principle says the more certain we are about where that electron is, the less certain we are about the electron's motion. So you can't make a measurement on position without affecting its velocity. I say velocity, momentum and velocity are linked, if you remember the equation. So I like to go back and forth. Whereas the more you're certain about its actual velocity, you're less certain about where its position is. That is the essence of the uncertainty principle. And of course, this is just a precision value. You don't have to worry about that mathematically. We're not going to look at that too much. So essentially, we're left with this probability cloud. We don't know exactly where an electron is, but we can calculate its probability of where we would likely find it, right? And that's the whole notion of this whole electron cloud. And that probability equation was described nicely with Erwin Schrödinger's wave function. So I'm not going to show you the wave function here. You can look it up. There's lots of different versions of it. I wasn't certain which version to show you, but at the high school level, since you don't know how to do partial differential equations yet, I kind of felt it would just be a waste to show it to you because it just looks like a bunch of symbols and you don't have to worry about it. But Erwin Schrödinger used his gifts with mathematics and statistics, and he was able to create an equation that accurately describes where we can expect with high probability to find an electron with enough given information. But even Erwin Schrödinger didn't really like this idea of not being able to know where the electron is, and the whole idea that it's under a superposition. And that's when he came up with his the Schrödinger cat thought experiment. I'm not going to describe it to you right now. I'm going to point you down below to where the description of this video is, which I don't write anything for the most part, and I'll make sure there's a link for the Schrödinger's cat video, because animations are always so much better. So when performing the double slit experiment, I'll leave you with this. With single photons, if either path is monitored, a photon passes through one slit or the other and no interference will be seen. So it behaves like a particle. They say the wave function collapses. As soon as you make a measurement, the wave function collapses and particles behave like particles, classically. If you do not measure it, so if you're not actually making the measurement of which slit the particle is going through, we say it goes through both slits simultaneously and therefore behaves like a wave. I'm going to stop this video about here, because then it leads into the Copenhagen interpretation of what to make sense of this, because this is the experiment that pretty much broke physics. Please read about the Copenhagen interpretation by going to this link here on the class calendar. All right, starts on page 34. It's been simplified to a paragraph. You should read about it. Likewise, I will make sure there's a video link down below for the Copenhagen interpretation, the many worlds interpretation. That one often gets misconstrued, so I'm not going to explain it because I might also misconstrue it. And the pilot wave interpretation. So those are the main three interpretations that most people look at when they're talking about quantum mechanics. Many of the physicists that I follow online, just through YouTube or just through podcasts, they tend to move towards, like Sean Carroll, for instance, he tends to trust that the many worlds interpretation is probably the correct interpretation, but it's almost impossible to try to prove any of them. So take it with a grain of salt. Watch those video links down below. They're about 10 minutes each. You can always speed them up in the options. Do watch them and email me any of the questions you possibly have on this matter. All right, thank you for watching.